Hi, my name is Andreas Teigland. I'm a Brew 21 PhD candidate at the Department of Geoscience and Petroleum. My project is automation and digitalization of life cycle well integrity. My background is from petroleum engineering, where I have a master's degree from NTNU. There are several aspects of well integrity, and I'm mainly focusing on casing wear. But to understand casing wear, we need to understand the drilling process. So this is a short description of the drilling process. We have the rig and the drill string and the casing. The drill string moves through the casing, drilling a hole into the formation below. But let's look closer at the interaction between the drill string and the casing. Here you see how the drill string is located in the well, as well as a cross-section of the drill string and the well. When we drill, the drill string is pushed against the casing wall with large forces while it's rotating. Over time, this will grind a hole into the inside of the casing, making it thinner and consequently weaker. And it's this weakness that we want to estimate when we're modeling casing wear. So how are they doing it today? It looks something like this. The current solution is to estimate casing wear in the planning phase. Then you use the parameters that you are expecting to use in the drilling phase. You're using planned parameters. After the well is drilled, you can log it and find out how much casing wear you actually have. The problem is when the planned parameters and the actual parameter deviates. Then you can get a big difference in the expected wear and the actual wear. What we want to do to solve the problem is to create a model that can model casing wear continuously while drilling by utilizing real-time data. By having a continuous estimate of casing wear, we can make changes to the planning if we realize that the casing wear will exceed the maximum allowable wear at the end of operation. So we did a case study on a well on the Norwegian continental shelf. We compared our approach to an approach performed by a company to validate if the well should be drilled or not. That analysis was done with planned parameters that they expected to use during the drilling operation. Those results are shown in orange on the right-hand side, where casing wear is plotted against measured depth. The estimates using real-time data is shown in blue, as well as the normal force in the well, the rotational speed, and the weight on bit. When we start the simulation, we can see how the drill string moves through the well, and how the weight on bit changes and the rotational speed changes. You can also see how the normal force is in the entire well. On the right-hand side, you see the casing wear increases as the well is being drilled, before reaching its final value at the end of operation. So these are the results. You can see casing wear calculated with real-time data in blue on the right-hand side, and calculated with estimated parameters in orange. It's apparent that the casing wear calculated with real-time data is significantly higher than the one calculated with planned parameters. The maximum difference is 3%, which is significant, as 3% as a rough rule of thumb would lead to a 3% decrease in the strength of the casing. Calculating casing wear with real-time data also results in a better match with logged values from the well. So what are the benefits? The obvious one is increased safety. By having a better estimate of the casing wear, you have a better estimate of the strength of the casing and a better estimate of the protective ability of the casing against the high pressures from below. You are also able to make decisions earlier before it's too late. Having a continuous estimation of casing wear allows you to make changes to the operational program in order to not exceed the maximum allowable wear at the end of operation. My project is sponsored by NTNU, and thank you for your attention.